So, like I said, if you're in physics class, AP Physics, you've already started talking about this stuff, right? And this is why you started talking about derivatives, so you could relate all of these things to each other. This is one of the more important concepts as far as applications in calculus go, and that's relating position and velocity and acceleration to each other. And then I threw speed in there because speed and velocity actually have slightly different meanings. Anybody know what the difference between speed and velocity are?
Direction. Speed is a scalar.
Okay, good. Speed is a scalar. Velocity is a
Vector.
vector, yes. So velocity has a direction, right? In general, give me 1 second. In general, we're going to talk about velocity in just a positive or a negative direction. You guys are probably, I don't know if you've gotten to it yet, but you'll deal with velocity in 2 dimensions. We're just going to go positive and negative with our velocity. So as far as the vector part goes, it has a quantity and a direction. The direction is just going to be positive or negative. Okay? And so the difference between speed and velocity is speed is the absolute value of velocity. It doesn't matter with speed if you're going forward or backwards. It's just how fast you're going. Most of the time we'll be dealing with velocity, but you'll have to know how to deal with speed in a few different ways as we go here. The first thing I want to talk about here is the terminology that we're going to use. Position tells us what? Position, right? Where it is. Now, how are we going to measure position? Because we want to quantify all of these things. We're going to represent them with variables. So what's that?
Coordinates.
With coordinates, right? So we might represent position as coordinates along some axis. So if we're talking about movement along an x-axis, then the position is just the x value, right? What variable do we use in physics? And this is a physics topic, so we'll be using the same variables. What variable do we use in physics for position?
X.
Use x or s?
X.
Use x? Really? Okay. Well, we're going to use s. Man. And to make it even more confusing, S actually stands for displacement. Yeah, exactly. Displacement is just a fancy word for position. And we can't use D because, well, distance or derivatives, right? We have differentials that use the D, so that would get really confusing. So we move to the next appropriate letter in the word. I is not good because it's the square root of negative 1, so we move on to the S.
Why do we use T?
We're going to use the absolute value of velocity.
That's the only time I make it.
Okay.
It makes so much more sense to use that.
Guys, we're going to use S. We're going to use S for displacement or position. Sorry, I know it does. Velocity, what letter are we going to use there? V. And acceleration? A. So let's talk about what each of those things means. Position just tells you where you are. Velocity tells you how.
Now we can't use S for speed.
Just calm down. That's just the way it is. Position tells you where you are. Guys, velocity tells you how fast you're going. What velocity is actually telling you is how fast your position is changing. Okay, if your position is changing really quickly, you're going really fast. If your position is not changing much at all, then you're not going very fast at all. So your position tells you where you are. Your velocity tells you how fast your position is changing or how fast you're going. Acceleration tells you what? How fast your velocity is changing. Exactly. So it tells you if you're speeding up or slowing down and by how much. Okay, if your acceleration is a high positive number, then you're maybe not only moving forward, but your speed moving forward is getting bigger and bigger and bigger. Okay, the good example here is if you think about what you're doing in your car, your acceleration, your car is accelerating, and it can be positive or negative acceleration, but your car is accelerating anytime the speedometer is changing. Okay, if the speedometer is staying still, if you've got your car set on cruise, then you're not accelerating, or your acceleration is 0. Anytime your speedometer is changing, that means that your car is accelerating. Even if it's going down, if your speed is decreasing, you're still accelerating, but your acceleration is, say it again. Didn't you say? Negative, yeah. So if you're slowing down, you're still accelerating, it's just a negative acceleration. Okay? So that's the end of the slideshow. Let me just get myself a blank sheet of paper here. Guess we're done for the day. Not really. So, now what's happening? Okay, so in calculus, and like I said, you already did this in your physics class, in calculus we can use the idea of the derivative to relate those three things together. We'll get to speed later. In fact, we're not going to really talk about speed anymore today. But as we said, your velocity, or the velocity of something, it doesn't necessarily have to be yours, the velocity is how fast your position is changing, right? Do you guys agree with that?
Yes.
Okay. Another way of saying that is the rate of change of changer? How fast position changes. Another way of saying velocity, or how fast position changes, is the rate of change of your position, right? Well, how do we measure rate of change in calculus? Derivatives. Okay, so since velocity is the rate of change of position, then we could write that as the derivative of I just used a different variable there. Why am I not differentiating with respect to x anymore? Why would I differentiate with respect to t? What do you think t represents? Time. So with all of these things, the independent variable is time. Okay, so just the movement of the clock kind of tells us what's going on with all this stuff. So we're going to take the derivative with respect to time of what to get velocity? It's how fast your position's changing, so it would be the derivative with respect to time of s, or we could just say ds dt. So velocity is just the derivative of your position. And the reason we differentiate with respect to time is because our position function, s, is going to be some function of time, and I'll write it like that. So that this function here would tell us what our position is for any time value. Yes?
Can we write a cursive S?
You can if you want, yes. Just don't make it look like an O or something like that. I see some bad S's that look like that. I don't know what that is. So make sure that I can tell what it is at least. Okay? Does everybody understand then why velocity is the derivative of position? Does that make sense?
Yes.
Okay. You guys should be an easy class today because you've done it already. Right?
No.
A lot of you have. All right, so velocity is the derivative of position, and velocity is a function of what variable? What's the independent variable we're going to use here? So another way of writing this would just be s prime of t is the velocity. Okay, now, Cole said it. Acceleration is how fast velocity changes. So if we want to know what the acceleration is at any time, what can we do? dv. That almost looks like a u. v dt. So it's the derivative of velocity with respect to time.
So it's kind of like taking
Or-
the second derivative of it.
Yep. So it's the derivative, the first derivative of velocity, but since velocity is the derivative of position, that means that acceleration is also the second derivative of the position with respect to time, or s double prime of t. So position just tells you where something is. The velocity tells you how fast that position is changing, or the rate of change. So if we take the derivative of position, we get velocity. And then acceleration tells us how fast velocity is changing. So if we take the derivative of velocity, we end up with acceleration. So the main point you want to pull from this, and I just wrote it down, but I'll do it again here. We have position. I'm not going to write anything for that. Then velocity is the derivative of position. And acceleration is the derivative of velocity, which is then the second derivative of position. All right, so this comes, well, it directly follows the last section in the book because they were talking about higher order derivatives. If we take the second derivative of the position, we end up with acceleration. So this is a good example of where we can take the derivative more than once and get something useful out of it. Okay, any questions about that? Like I said, I'm not really going to talk about any of the math specifics yet, but it's important to understand how they fit together. I do want to look at it from one other perspective real quick, and that's graphically on a graph, because the graphs are really important in this class, and to understand what's going on in a graph is one of the more important things that you can do here. So if we have a graph of something drawn with respect to time. So let's say the position of some particle is represented by this graph. And I wanted to know how fast that particle is moving at some particular time. I want to know how fast that particle is moving, say, at this time here where t equals c. Okay, so at that point right there. I know where the function or where the particle is. I can figure out where the particle is by going over here on the y-axis, and this would be my position at c. But that position doesn't tell me how fast the particle is moving. How would I figure out how fast it's moving? Find the slope, right? You guys used the formula before, distance equals rate times time. Well, that's an average rate of change. We want to find the slope of a tangent line. So if we find the slope of the tangent line at that point right there, and this is actually a special kind of point, it's an inflection point. I think it was Evan that was asking me about them before, where the tangent line actually goes through the graph here at this point. But if we find the slope of that tangent line, that's going to tell me how fast the particle is moving at that particular point. Now, let's talk about why that works as far as units. Let's say our position here is measured in meters, and our time here is measured in seconds. Then what would be the units on the slope? So the slope is the change in s over the change in time. And I think this is really interesting too. You can see from this why we're taking the derivative with respect to time. Delta is a Greek letter for d, right? So another way of thinking about this is ds dt, the derivative of position with respect to time. That's kind of cool, isn't it? But not only that, the change in position is going to be what units? What are the units in position? Meters and per second, right? What do meters per second measure? Velocity. How fast you can go in 1 second. Or, I'm sorry, how many meters you can go in 1 second. Okay, so that's a measure of velocity, meters per second. All right, now, if I change this here and I said that this now, instead of being position, is velocity, and we're measuring that velocity in meters per second, and I still have time along the x-axis, Now, instead of finding the slope to find the velocity, I'm finding the slope to find the acceleration. In this case, we're going to take the change in velocity divided by the change in time, and what are the units going to be here? Yeah, so it would be meters per second, or meters per second squared, and that is a unit of acceleration. Meters per second means it's how fast the position is changing every second. Okay, so meters per second is a speed, and the speed changes every second by whatever amount. So meters per second squared is telling you how fast the speed is changing, which is why meters per second squared is an acceleration unit. Okay, any acceleration unit is going to be a distance divided by a time times a time. It could actually be like miles per hour per second. That would be acceleration. Usually it's written as some time unit squared in the denominator. Okay, any questions about any of that? You guys remember on the second test, I guess, I asked you to do units in a coordinate plane like this?
Yes.
Some of you may remember that, I guess. This is why. If you understand what's going on with units in the coordinate plane when you're taking derivatives and integrals, it's going to really help you keep things straight and understand what exactly it is that you're finding when you do calculus, when you take derivatives and integrals.